Hi and welcome to this Leaving Cert Higher Level Maths video. We're focusing on calculus, and in particular we're going to look at rates of change, related rates of change and some real life examples. So just to be clear, this video is going to cover both differentiation and integration. If you haven't yet done integration, you can still watch this. It will make a little bit of sense. I have noted the example where integration is used. Otherwise, we are just looking differentiation. I'm going to link below some basics of integration and basics of differentiation. I strongly recommend if you're revising that you revise these first. So let's talk about rates of change. When we're studying calculus, we're basically looking at how variables change. So we are always looking how things change. That is what calculus is. But now we're going to look specifically of how these change with respect to time. So what is required to know is this relationship between distance, speed and acceleration. There's very few things that we are expected to know in the maths course apart from the maths itself, but this is one of them. So let's talk about distance, speed and time. You would have studied this at junior cert in both maths and science, and hopefully everyone is familiar with this DST triangle or using the formula in some way. So distance is speed multiplied by time. Speed is distance divided by time, and time is distance divided by speed. This is known as Dad's silly triangle, and it's a way for us to figure out which formula we need. Now, when we talk about distance, speed and time from the junior cert, really this is a very simplistic view because it ignores acceleration. It basically assumes in all questions that there's no acceleration and that speed remains the same. So when I'm looking at a junior cert question and it's talking about traveling from one place to another, effectively what they're assuming is you jump into the car when it's moving and you jump out of the car while it's moving and the car remains at this constant speed. Now, the reason it's simplified is because at junior cert, the maths you know is a simpler version of what we now know. So what we're moving into is embracing this acceleration. So we're now going to be more accurate with our calculations because we are going to be able to deal with acceleration. When we talk acceleration, what we mean is how quickly your speed is changing. So if you're driving or if you're learning to drive, we talk about the accelerator in the car. So it's the thing that makes you speed up. So we have an opposite to acceleration, and that is deceleration or braking if you think of it in terms of the car. I'm going to talk a little bit now about displacement, velocity and acceleration. This is not maybe specifically something you need to know, but I think if you know what I'm going to go through in the next few slides, it will make this whole section so much easier. For anybody who studies physics, this is something you already know. For anyone who studies applied maths, again, you'll know all this, but just be aware that we don't use the formula that you would use in physics and applied maths in our course, so the Leaving Cert Higher Level Maths course. We're not going to use that. Also, there is an assumption in physics and in applied maths that the acceleration is constant. We don't have that. We don't necessarily have that limitation with us here. So just if you're kind of going, oh yeah, I know all this, just bear with us. It's not identical in the way that we'll actually do these calculations. And sometimes I see students try to use the equations of motion. Please don't use them. So I'm going to talk to you about displacement, velocity and acceleration. So displacement is distance traveled in a given direction, and velocity is speed in a given direction. So basically, we're going to rename what would have been distance and speed as displacement and velocity. Now, this renaming is not constant. A lot of the books will still use the word distance. A lot of the books will still use the word speed. I try to use both when we're working through the notes part here. But I suppose the difference between displacement and distance is if I am standing at one end of a football pitch and I walk to the opposite end and I walk back, I've travelled a distance. However, displacement, have I now been displaced from where I originally was? If I'm back where I originally started, there's actually no displacement. So although in most cases displacement and distance are pretty much the same, they are slightly different. Velocity and speed. Now, velocity is a word that we see a lot for speed, and it just means speed in a given direction. So it's not necessary that I travel 20 miles an hour or 20 kilometers an hour. It's 20 kilometers an hour north. Now, the reason I'm getting into this is because both of these, displacement and velocity, are what we call vector quantities. Again, if you do physics, if you do apply maths, you're going to be more familiar with this. If you don't, you've probably never heard of a vector. But basically, a vector is something that has magnitude, so a number, and also a distance or a direction. The reason I keep bringing this back to the fact that we have vectors and this subtle difference is because in our answers, we can get negatives. So if I have a negative speed, that's nonsensical. That makes absolutely no sense to us. But negative velocity means I'm going the opposite direction to what I originally was going. Displacement, if negative, means it's again an opposite direction. So a negative really means direction, and it's so important that we understand that, what that negative implies. It is the direction. Now, we have seen it a few times on our paper where this negative comes in, so it is something you need to be aware of. So acceleration is also a vector quantity, and when we see this as negative, what that means is it's deceleration. So the speed is going down rather than up, and that's that idea of direction. So just to be aware, speed and distance are known as scalar quantities, so they would have no direction. Now, I've made a big fuss about the difference here, but I suppose it's important in one instance to understand what happens if we get a negative. It's also important to understand if you see these words, displacement and velocity, what actually they mean. The next thing that it helps us to understand is the use of letters, because we're so used to seeing that capital D, the capital S, and the capital T for distance, speed, and time. That's going to change now because velocity is used instead of speed. So often, even if they use the word speed, they are talking about it as a V rather than S. Okay, so V, and it's lowercase. V stands for velocity. So velocity or speed is how far a body travels, so this displacement or distance, in a given time. So basically how the displacement changes over a given time. If we think of displacement with a lowercase s, and this might feel mad, but again, we're bearing in mind our letters are changing as well as these words. So displacement is defined with this lowercase s, not to be confused with the capital S, which we used for speed. That's gone. Remember, instead of speed, we now have velocity, we now have V. So if we define displacement with the lowercase s, then velocity is differentiating s, so differentiating displacement with respect to time. And that is how we get our rate of change. So how fast is that displacement changing? So if we're moving quickly, that means we are going faster. So we differentiate s with respect to t, ds dt. So if I gave you an equation, or if I defined s equals to something with a t, we would differentiate that the exact same way as we have been differentiating our dy dx. All that's happened is we've changed our variables to s and t. So our acceleration, you'll be happy to know, is defined by a lowercase a. So we have velocity, v, displacement, lowercase s, and acceleration a. This probably makes the most sense. Acceleration is a. So acceleration is how fast or how much the velocity or speed of a body is changing in a given time. So again, if we define velocity with our v, our lowercase v, and then our acceleration is given by dv dt. So we differentiate v with respect to t. So if we think of our starting point as displacement or distance, which is the letter S, we then want to get to velocity and finally get to acceleration. And this is often how I would have this drawn out on the top of a question. It's just S, the V, the A, you don't need the words. You can, of course, put the words, but it gives us a nice kind of nearly flowchart to direct us how to do a question. So if I want to move from displacement to velocity, I am differentiating, and it is ds dt because it's with respect to time. If I want to move from velocity to acceleration, again, I'm differentiating my velocity with respect to time, dv dt. And there's another way we could think of this, which is imagine going straight from displacement to velocity to acceleration, which is we differentiate s and then we differentiate that answer, which would give us a second derivative of s. So dv dt or d squared s dt squared, so our second derivative of s. Either is correct, and it'll depend on the question. You can think of it in either way. This is just a second derivative. So then what if we want to move the other way? So acceleration back to velocity. Well, if we differentiated to get from velocity to acceleration, to get backwards, we're going to do the antiderivative, which is integration. Okay, so we're going to integrate. So the velocity is when we integrate acceleration with respect to t. And from velocity back to displacement, it's where we integrate our velocity with respect to t. So this little flowchart, we go from displacement to velocity to acceleration using differentiation. We come back up, so from acceleration to velocity to displacement using integration. So let's look at an actual question. This first example only contains differentiation, no integration. A body moves in a straight line so that its distance s in meters from a fixed point after t seconds is given by this equation. Notice they've used distance and not displacement, but this is not an exam question, okay? In an exam question, I wouldn't expect them to use distance, but they could. The first thing it asks us to do is find the speed after 2 seconds. So we would first of all start with our s. We have our distance. Now, if I want to figure out how fast something is going, I'm going to need its velocity. Just be careful with this s here. So we start with s, we then come down and we get our velocity, and then acceleration is at the end. I want velocity, v, which is speed. I have s, so what I'm going to do is differentiate it. So I'm going to do ds dt. So I differentiate this whole function s with respect to t. So what that means is the t is the thing that I apply the rules of differentiation to. So the 10 is a constant, it disappears. 27t just leaves me with 27, and minus t cubed minus, bring down your power and take away 1 from your power. So this little formula that I have made represents speed. They didn't want a formula for speed. They wanted the speed after 2 seconds. So now I'm going to sub in, instead of t, 2. And this gives me an answer of 15. Now we started with meters and seconds. This is our velocity or speed. So it is 15 meters per second. Make sure you include your units. The second part of this question then says, after how many seconds is the body at rest? So rest means there is no speed. So basically, I have my formula for speed, which I noted clearly in part I. I would strongly recommend that you do that in a question, because if there's multiple parts, coming back to a previous part to find your answer, you're in an exam, you're stressed, you're trying to find it. If you have something clearly written, like where I've written speed, then you can find it a lot quicker. And this kind of question, it's very short. It's not going to make a huge difference, but with the layout of our exam papers, it's something that will help. So this is saying the body is at rest, so speed is 0. So basically, they want us to solve this. Now, we have 3t squared minus, or 27 minus 3t squared. I prefer to work with 3t squared minus 27 equals 0. And there is a 3 in common, so I'm going to divide by 3. The reason I'm not pulling that 3 out as a highest common factor is because it's a constant. You can pull it out, but it's not going to be helpful. We would never divide across by the variable. We would only ever divide across by a constant. So that leaves us t squared minus 9 equals 0. And hopefully at that point you will figure out that we have a difference of 2 squares. If you don't, and you work this differently, you would have probably still ended up with your t equals 3. You might have forgot your t equals negative 3, but because it's time, this is not valid. So after how many seconds is the body at rest? It is at rest after 3 seconds. So part 3 then, find the acceleration after 2 seconds. So again, we started with our distance, we moved on to our speed, and then we get acceleration. So we already have our speed. So I'm going to call that v. From our previous part, it was 27 minus 3t squared. To get my acceleration, I'm going to differentiate this. So I'm doing from v to a. So I'm going to dv dt. This is only notation. If you prefer, you could write this as the second derivative of s. That's absolutely fine. So my constant disappears. I bring down my power and I take 1 away. So it is minus 6t. So then I don't want it in terms of t. I want it after 2 seconds. So that is minus 6 times 2, which is minus 12. And acceleration is meters per second squared. So if you're doing this, you think, well, actually, how can that be a negative? And the answer is because it's actually deceleration. What's happening for us here is what have we got? The body is actually slowing down. If we were to plot the velocity itself, so this velocity here, if we were to plot this, this is a negative quadratic that looks like this. It has 3 and negative 3. We worked this out. So we have an x-axis that represents t and a y-axis that represents our speed v. But we live in the real world where time can only be positive. So we can only deal with this part of our graph. This bit is redundant. And look what's happening. We're getting this slowing down to the point of it either stopping or reversing. It will, when we see this like negative velocity, it would end up reversing itself. So that minus is implying that it is a deceleration. So minus 12 meters per second squared. So example 2 is another rates of change question, and this time it's going to include integration. So a body moves in a straight line. At a time of t seconds, the acceleration is given by a equals 6t plus 1. When t equals 0, the velocity of the body is 2 meters per second, and its displacement from a fixed point O is 1 meter. Anytime we get a statement like this, we are getting a pretty big hint that it is an integration question. Remember, when we integrate, there will be the constant, which we have that plus c. And when we have that plus c, It represents some number that we don't know. So in order to figure out what that number is, we actually need to have a bit more information. So that statement there is telling us when t is 0, the velocity is 2, and our displacement is 1, and that allows us then to get rid of the constants and instead have a solid or a constant number. So let's put up our little flow chart. So we start with S, which is displacement, and then we have velocity, and then we have acceleration. We actually have started here with acceleration, and we want to find expressions for V and for S in terms of t. Okay, so let's start with our acceleration. So our acceleration is 6t plus 1. So in order to get my velocity, I'm going to integrate this 6t plus 1 with respect to t. So when we do that, we're working backwards. So we have t squared, and we're going to divide the 6t squared by this new power plus 1t divided by 1, which is just t, plus c. So plus some constant. Now, this is where we're going to use the yellow statement above to figure out what the constant is. So it says when t is 0, the velocity is 2. So when I sub in, so v is 2 when t is 0. So 2 equals 6 times 0 over 2. You can simplify that if you want. Plus 0 plus c. Therefore, c equals 2. If you were comfortable, you could go straight to c as 2 because they've given us t equals 0, which is effectively the y-intercept, which means that 2 represents the constant. So you could go straight to there. So v is going to be, and I'll clean this up now, 3t squared plus t plus 2. So that's an expression for v. Now let's get an expression for s. So I'm going to work s over here. So s is going to be where we integrate v. So this is 3t squared plus t plus 2 with respect to time. So that gives me 3t cubed divided by 3 plus t squared divided by 2 plus 2t plus c, so our constant. In order for us to fill in this constant, they said when t is 0, the displacement s is 1 meter. So we're going to need to sub in here. Again, same rule applies if you spot it. They've given us t is 0, so 3, 0 cubed over 3 plus 0 squared over 2 plus 2 times 0 plus c. So that gives us c equals 1. So it's still another way of giving us the y-intercept. So our final s is equal to, when I clean it up, t cubed plus t squared over 2 plus 2t plus 1. And I'll just box this, and actually what I might do is I'll just throw a highlighter because there's quite a lot here. So there's our v and there's our s, both in terms of t, both without that plus c. Now part 2, it says find the velocity of the body after 4 seconds. So we're going to take our velocity formula that we've worked out in the previous part, which is 3t squared plus t plus 2, and we're going to do this when t equals 4. So the velocity is 3 4 squared plus 4 plus 2, and that gives us 54, and it's meters per second because they'd already told us earlier in the question that it was meters and we were dealing with 4 seconds. So now let's look at an exam question. This exam question asks us to look at a velocity function, but it's in 3 different parts. So this caused a lot of problems for students, but it is very, very realistic. And actually, when we break it down, it makes so much sense. So a sprinter's velocity over the course of a particular 100 meters race, that's important. We have 100 meters. So 100 meters, so that's the full race, is approximated by the following model, where v is the velocity in meters per second, so we're dealing meters per second, and t is the time in seconds from the starting signal. So the velocity is at the start 0, from 0 to 0.2 seconds. Then it's defined by a negative quadratic for 0.2 to 5 seconds, and then it's defined as simply 11.52 for t is greater than or equal to 5. So what that means is, as the starting gun is fired, it takes 0.2 seconds for a sprinter to react. They then are going to go, and I'll sketch it out here. So this is going to be a little bit exaggerated, but it'll give us a sense of what's going on. So it takes a minute to react, negative quadratic. So what's happening is they are accelerating very fast, and then their acceleration gets less and less and less until they hit what would really be their maximum speed, and then they're going to run that for the rest. Now, you could argue, will they keep going that maximum speed? It's 100 meters, so I assume that because it's a sprint, they can. And that's the assumption here in the question. So that's the 3 parts. So part 1, the reaction, okay, or the lack of reaction, the time it takes to react. We then have that negative quadratic, and then we have that constant speed. So the negative quadratic, what it's doing, it's representing somebody who is accelerating very quickly and then accelerating less and less and less. And the reason I'm saying that is because I'm looking at the slope. It's much steeper at the start, and it gets less and less steep. So we want to fill in this graph. It's going to look something like what I've just drawn, but we need to be a bit more accurate. So 0.2, so it works along here. So that's the reaction time. Using the quadratic, we're going to fill in 1, 2, 3, and 4. I don't need to fill in 5, because when it's equal to 5, it's going to be 11.52. So there's 11. So it's going to be about here. That's, I think, 11.52. And then it's going to be at a constant. Now, I apologize, I haven't got a ruler to work on here. But it's going to be constant like that. We do need to show the points in between. So 0.2 is going to be here. So let's make a little table to just work out. So we're going to do V of 1. We're going to do V of 2. We're doing V of 3. And we're going to do V of 4. And we're using minus 0. We're using this V of t. Minus 0.5 t squared plus 5t minus 0.98. So when we sub in 1 to there, I'm getting 3.52. When I sub in 2, I get 7.02. When I sub in 3, I get 9.52. And when I sub in 4, I get 11.02. Now, you can sub in 5, but there'll be no way that you can go from having one speed to another speed without climbing continuously through the speeds, but you can always double check. So now we're going to plot. So 1, 2, 3.52-ish, 7.02, so about there, 9.5 or about here. Oh, it doesn't want to mark it. Yeah, I think we're about there. And 4 is 11.02, so just about there. So we end up with this negative quadratic curve which joins to that straight line, and we're going to label this v of t. So then part 2 says find the distance travelled by the sprinter in the first 5 seconds of the race. Okay, so in the first 0.2 seconds, they don't move. Remember, they're reacting. Then in the next 5 seconds, we're dealing with the middle function. So I'm just dealing with this part here, minus 0.5 t squared plus 5t minus 0.98. That is velocity or speed. Notice that they've said distance and they've used velocity, so they've used a bit of a mix. So S, displacement or distance, V, velocity, A, acceleration. We have velocity and we're trying to find the distance. So we're going backwards. So because we're going backwards, we're going to be integrating. So S is going to be when we integrate minus 0.5 t squared plus 5t minus 0.98. Now, we're doing that with respect to time, and we would generally have a plus c like we did in example 2. However, because we've been given what this is valid between, we can actually use definite integrals here. So between 0.2 and 5. So instead of doing a plus c and then subbing in, and we can sub in when t is 5, the velocity is 11.52, you can of course do that to find c. This is just a little bit neater. Because of the way it was asked, I think it's much easier to just use your definite integrals. If they don't give you the limits of the integral, so obviously, then don't worry. Just go and work out the c the way we did. But I think this is a much nicer, more efficient way to work. So when we integrate, we have minus 0.5 t cubed, when we're adding 1 to the power, dividing by the power, plus 5t squared over 2 minus 0.98 t, and we are doing this between 0.2 and 5. So we sub in for 5 and we sub in for 0.2 and we take them away. There is no need for a plus c. So when we do that, we're going to have minus 0.5 5 cubed over 3 plus 5 times 5 squared over 2 minus 0.98 times 5. We're then going to take away, subbing in the 0.2 cubed over 3 plus 5 times 0.2 squared over 2 minus 0.98. I'm going to space, I'll move this down a little bit, minus 0.98 by 0.2. That works out as 36.77 minus watch your signs, 0.0973. You can leave them in fractional form if you prefer. And actually, I've simplified it, or rather I've rounded it there by putting it to decimals, but if we were to use the fractions, which is 1103 over 30 and then 73 over 750, it works out not evenly but correct to 3 decimal places without rounding, which is 36.864 meters. Because they didn't actually ask us to round it, it is probably better to use the more accurate version. If you then, instead of that, you took my decimals, it would have been 36.8673. So it would be slightly out. We would be correct to 1 decimal place, but the 2 decimal places would disagree. So this to me will be a more accurate answer. So part 3 then is find the sprinter's finishing time for the race. Give your answer correct to 2 decimal places. Okay, so by this part, what we know is in 5 seconds, we have run, and I'm going to work with that more accurate answer, 36.864 meters. So then what's left to run, we're going to take that away from 100. So we'll do 100, because remember it's a 100 meters race, take away 36.864, and that leaves us with their 63.136 meters left to run. Now, the good news is this is a constant speed. So we don't have to worry too much about this because there's no acceleration. The speed is a constant. The speed is a number. To figure out the time, we're going to take the distance that's left, the 63.136, and divide it by the velocity, 11.52. This is a throwback to our distance, speed, time triangle, and we are left with 2 decimal places, 5.48 seconds. So it takes 5 seconds to get up to this point here. It takes 5.48 more seconds. So then to get his finishing time, or hers, so the sprinter's finishing time, we're going to have 5, the initial 5 seconds that we dealt with in part 2, and 5.48, which gives us 10.48 seconds, correct to 2 decimal places. So when we work with our displacement, our velocity and acceleration, and if you've worked through the last few examples, you'll see that we get a formula in terms of t, just because they can be represented as a function in terms of t. But not all measurements can. And that's where our related rates of change come in. So when we're given the rate of something, and this is probably the key to the question, when you see that word rate in one of these questions, we're calling that d something dt. And the reason I have a question mark there is because it's going to depend on the question. It might be the rate at which the area, so dA dt, the rate at which the volume, dV dt. It will depend on the question, but it'll all come back to this idea of d something dt. So example 4, the radius of a circle is increasing at a rate of 2 centimeters per second. So as soon as you see that word rate, we know we're dealing with d something dt. D something dt. It was the rate of the radius, so I'm going to call that d or dt. And the fact that it's increasing tells us that it's going to be positive. Anytime we see it decreasing, we have to take account for that. We'll put in a minus. It says find the rate at which the area is increasing when the radius is 3. So we're dealing with a circle. So the area of a circle is pi r squared. You can get that in your log tables. Now, if I want to find the rate at which the area is increasing, rate is dA dt. So they want us to find the rate at which the area is increasing. So they want dA dt. That's what we're being asked. Now, the problem is, and we didn't run into this problem when we were dealing with displacement and velocity and speed and acceleration, is I can't do dA dt because the formula for A doesn't have a t. And this is why we need these related rates of change, because it's not as simple as I just differentiate. Because if I was to come along and do dA dt, it's like, well, there is no t. What can I do? And this is what I will do. So there's a few different ways that we can approach this. I like starting with the formula and doing what I can with it. So I have a radius, so I'm going to do dA dr, because that is a variable that's there. Remember that pi represents a number. It's just 3.14159, but it is just a number. So the only thing I can differentiate A with respect to is that or. So I'm going to bring down my power 2 and take 1 away from the power. So I get 2 pi r. So I have a dA dr here. I was given dr dt and I want dA dt. So let's start with what I want. What I want is dA dt. Then what I have is a dr dt. I now need to use something, which is something over something, to make this equation work. I have a dA dr. If I fill that in as is, dA dr, will this work? And the answer is yes, because I have dr on the bottom, which cancels with the dr on the top. And I multiply across and I get dA dt. Okay, so what I need to do to figure out my dA dt is dr dt, which was given to us as 2, multiplied by dA dr, which I worked out, which was 2 pi r. And my answer is 4 pi r. And that is the rate at which the area is changing. Now, they've gone a step further and asked us to do this when the radius is 3. So when r is 3, we're just going to sub that in. So 4 pi 3, so we get 12 pi, and the area is going to be centimeters squared per second. You can sub in that pi. I'm going to leave it in terms of pi. If it was an exam question, they would tell you what you need to do. So let's try another related rates of change question. The volume V in centimeters cubed of water in a container is given by this expression. So this is my volume formula. Sometimes we'll have to go and get a formula out of our log table. Sometimes they'll give it to us. They tell us that H in centimeters is the depth of water. Water is flowing into the container at a steady rate. Okay, so rate, this is going to be d something dt. Now, water is flowing and it's centimeters cubed. So this is dV dt because it's the volume of water. Area of water doesn't make sense. So it's the volume of water. And look at that centimeters cubed. That's giving you a big hint because when we talk about cubed, centimeters cubed, meters cubed, we're talking volume. It then says, find the rate in centimeters per second at which the depth of water is increasing. So D, the depth of water, H is increasing, so dt. That's what we want. Okay. So just like before, so we have dV dt, and that is 90. dH dt is what I want. We've been given this formula. I can't go and do dV dt. I can do dV dH, which gives us 24H. Okay, so this is important, and then this is what I want. So let's start with what I want. I want dH dt. I was given dV dt. That's what I was given. I then need to multiply it by something to make this correct. So if I have the dt, now I have a dv up here, but I don't really want a dv because I want actually a dh. So to cancel that, I'll want a dv down the bottom because then they'll cancel, lovely. And then on the top, I'll want a dh, so I have my dh here. So I want dH dV. Now, I don't have dH dV. I have dV dH, but they're very similar. One is simply reciprocal of the other. So if I want dH dV, I flip that side, I flip the right-hand side. So it's 1 over 24H. So to work out dH dt, the thing I want, I use dV dt, the thing I was given in the question, and I multiply by the dHdV, the thing I worked out that I needed. These are called partial derivatives because we're using bits to create what we want. Multiply across the top and across the bottom, and we can simplify, and I get 15 over 4h. So it was really 90 over 24h, but we can simplify. So we can simplify the top and the bottom. 6 goes into both. Again, this is giving me the rate at which the depth of water is changing. I actually want it when h is 3. So let's work when h is 3, which gives me 15 over 4 times 3, which is 12. So 15 over 12 gives us 5 over 4, or 1.25. I've gone a bit too close. So, or 1.25 centimeters per second. Let's look at an exam style question where we were asked about these related rates of change. Air is pumped into a spherical exercise ball at the rate of 250 centimeters cubed per second. Again, we're being given a rate. This is d something dt. So what is the something? Air is pumped into an exercise ball. Hint really is that centimeters cubed. We're talking volume. So they've given us dV dt is 250. Find the rate at which the radius is increasing. So the thing we want is dr dt, the rate at which the radius is increasing when the radius of the ball is 20. Okay, so we have a sphere. We're going to need to figure out something about the sphere because we're missing one piece of information, and that is the volume formula. So in your log tables, on page 10, the formula for the volume of a sphere is 4 over 3 pi r cubed. How did I know that I wanted the volume formula? Well, we have two variables given here, dv dt. So we have v, and then dr dt. We have r. There is no formula for a radius, but there is a formula for the volume of a spherical exercise ball, i.e. a sphere. When we take that volume, we look at it and say, well, I can't work out dv dt because there's no t in it. But what I can work out is dv dr. So I have dv dr. I'm differentiating this with respect to r, multiplying by 3. So bring down your power, take 1 away from your power, and when we simplify this, we get 4 pi r squared. So that's dv dr. Okay, so I have dv dr that I've worked out, dv dt, the thing I want, or the thing I was given, and dr dt, the thing I want. So dr dt, the thing I want, is equal to dv dt, the thing I was given, and I need to fill in a second fraction or partial derivative. So I look at this and I try to figure out, well, what will work? So I have my dt's, that's fine. I don't want my dv, so I'm going to bring the dv under the line because then these will cancel. And I do want a dr, which I don't have, so I'm going to have dr up here on top. So I want dr dv. I don't have that, but I have dv dr. So dr dv is simply flipping it. It is the reciprocal. So 1 over 4 pi r squared. So dr dt is equal to dv dt, the thing that they gave me in the question, multiplied by dr dv, 1 over 4 pi r squared. Multiply that across, we have 250 over 4 pi r squared. We can simplify this to 125 over 2 pi r squared. They asked us to do this when the radius of the ball was 20. So we want when r is 20. So when we sub that in, 125 over 2 pi 20 squared. Now, just to be mindful that they asked us to give our answer in terms of pi. So we want to leave pi in our answer. If you go to your calculator and you type in what's currently there, so 2 pi and then 20 squared, what you're going to get is a decimal. It's not going to leave it in terms of pi. So one way around this is by simply ignoring the pi. So take the pi out of the calculator. So what I'm typing into my calculator is 125 over 2 times 20 squared. It gives me 5 over 32. And then I can put in the pi, remembering that the pi goes underneath. So apologies, I'm going to have to move up here because I'm running out of a bit of space. So simplified in my calculator as 5 over 32. Pi is in the denominator, so I put pi back into the denominator. And that is the rate at which the radius is increasing when the radius of the ball is 20. So part 2 of this same question says find the rate, okay, d something dt, of which the surface area of the ball is increasing. So we want dA dt, where A is surface area, when the radius of the ball is 20. So it's the same, not restriction, but it's the same measurement that we've been given. Radius of the ball is 20. So these two parts are connected. So bear in mind that we can use our answer from the previous part, which was d or dt, and we worked that out as 5 over 32 pi. The reason I can use it like that and not just the formula is because we're dealing with the same point in time, i.e. when the radius of the ball is 20. So this is, well, the follow-on question is a little bit more challenging because it's not as obvious. In the first part, it said the air pumped in at the rate of 250. So they explicitly told us, while the thing that they told us in this part was actually your answer from the previous part. It wasn't as obvious. So we want dA dt. We've been given d or dt. So I need a third piece of information, which I'm going to do by getting the surface area formula from page 10 of my log tables, which is 4 pi r squared. I can't just go and work out dA dt because there is no t in that formula, but instead I'm going to work out dA dr. When I do that, I bring down my power 8 pi r. So now I want dA dt. I have dr dt. I need to then multiply it by something that will make this equation balanced. It will make it the same on both sides. I have my dt, and my top line has a dr that I don't want. So I'm going to have dr down here on the bottom, and I wanted dA. So I'm going to multiply that by dA dr, which is exactly what I had worked out. dA dr. No flipping required. So dA dt, the thing I want, the rate at which the surface area is changing, is dr dt, which we've worked out, 5 over 32 pi, multiplied by dA dr, 8 pi r. If you want, you can put that over 1 to make it easier. The pi's cancel. We can simplify that. 8 goes into 8 once, it goes into 32 4 times. We get 5 r over 4. But remember, we want when r is 20. So this is going to be 5 times 20 over 4, which is 25. And this is area centimeters squared per second.